Hello and welcome dear students, and now we are going to discuss few more numericals on bolted connections for your understanding, and also we are going to discuss one more topic that is left, which is the eccentric connections and how to do the design of eccentric connections. So let us start with this numerical, and here it is given that there are two cover plates and it is the 10 mm and 18 mm thick are connected by actually here it should be main plates, and two main plates of thickness 10 mm and 18 mm thick are connected by a double cover butt joint using 6 mm cover plate as shown in figure 3.20. Find the strength of the joint given that M20 bolts of grade 4.6 and Fe415 plates are used. Okay, all the data are given and this is the diagram. So this diagram you have to understand very clearly. So as I said, it is the main plate. Main plate is this on which we apply basically the loading axially. So this is the main plate and these are the cover plate. Okay, so the thickness of cover plate is 6 mm and the main plate thickness is 18 mm and 10 mm. So there is difference in thickness of main plates, so to connect them we have to use a packing plate, isn't it? You remember this special type of joint in which we are going to use the packing plate. So what will be the thickness of packing plate? TPK will be equal to 18 minus 10 and it is equal to 8 mm, which is of course greater than 6 mm as per the code's recommendation. So we have to apply the factor beta TPK. Okay, so this is what about the packing plate and the reduction factor which we have to incorporate on the shear capacity of bolted connection. Now you have to see there are two rows of bolts and there are 3 bolts in each row, so we have to basically multiply with the design strength of one bolt, which is the minimum of bearing and shearing, with the total number of bolts, that is 6. Okay, and you have to see all the parameters values given here. This 40 is the end distance, this is the pitch, this is the gauge. Now after taking this 8 mm thick packing plate, what we can do, we have to calculate the reduction factor beta pk, and beta pk is given by this formula of the IS code. Okay, so we just have to multiply it here and reduce it from 1 and it comes out to be 0.9. Now this beta pk will be multiplied to the formula of shear capacity of the bolt. Now let us calculate also the nominal shear strength of one bolt in double shear. Okay, so it is not given in the question as such, but you can also assume here. What is assumed that one shear plane is lying in the shank area and one shear plane is lying in the threaded area. Okay, so the same thing is here done and VNSF is calculated here as beta pk. This is VNSF, this is multiplied with beta pk because we have put here beta Lj is equal to 1 and beta Lg is equal to 1 because at such long joint or large grip length, at such these things are not given. Okay, so we just have put them equal to 1, but we will multiply it with beta pk because it is equal to 0.9 and this is multiplied by FUB by root 3 into NN ANB plus NS ASB. Okay, so the same thing is done here, 0.9 into 400 by root 3 into 1.78 pi d square by 4, and this comes out to be this value of VNSF. Now this is nominal shear capacity of one bolt and we have to divide it by partial safety factor to get VDSF, design shear strength of bolt, and then we have to multiply it with 6 number of bolts in the joints to get total shear strength of joints. Okay, this is shear strength of joint in shearing. Okay, so this value obtaining is not very difficult. Now we have to calculate the bearing strength of the joint, bearing capacity of joint. So first of all we have to calculate the value of kb. Kb is minimum of these four values. So when we put all these values in these four different values, then we get the minimum value kb is equal to 0.606. So we can easily put it in the nominal strength of one bolt in bearing, which is equal to 2.5 kb dt into fu, and fu is fub here. Okay, so although here it is used 410, but I would suggest you to use 400 only. And we have put all the values. 2.5 kb is 0.606, and d is the diameter of bolt, t is the thickness of plate. Now why we have taken thickness of plate is equal to 10 mm? Because we have to take the minimum thickness of plate. I have told you, if there are two plates of different thickness, then you choose the minimum thickness of plate, because the minimum thickness of plate will give you minimum strength, and this is what you want. You don't want larger strength. Okay, so you want only minimum strength. You want to determine minimum strength, because the thicker plate will not fail. It will be the thinner plate who will be failing. Okay, so that's why we have taken here the value of thickness is equal to 10 mm. Now if you calculate it, you can get this value of VNPB is equal to this value. I hope this is very clear to you. Now this is for only one bolt, and also we have to calculate the design bearing capacity of bolt, and it will be obtained by dividing it by partial safety factor and then by multiplying it with the total number of bolts. So this is done, and this is written in kilonewton. Okay, now what you see, this is the value of design bearing strength of joint. Okay, bearing strength of joint. Now if you see bearing strength of joint and shearing strength of joint, there is not much difference, but you see shearing strength of joint is equal to 0.557 and bearing strength of joint is 596. So from the comparison we arrive that strength of bolts in connection will be minimum of the two, and it is equal to 557.896 kilonewton. So this becomes the strength of the bolted connections. Now we have to also calculate the strength of plates in the joint, and the design strength of plate will be equal to TDN. So let us calculate TDN, and TDN is equal to 0.9 AN FU by gamma m. Now calculation of this net area of plate is very important, because there are 3 holes done in the plate in one row. So this is a chain bolting, so we will use directly the formula B minus N DH multiplied by the thickness of plate. Okay, and here thickness will be again the minimum thickness, that is equal to 10 mm. And this width B value, how to calculate this value of B? This value of B is given in the question itself. You can obtain this by doing the summation of all these 4 values, and when you do this you arrive at B is equal to 40 plus 60 plus 60 plus 40, and it is equal to 200 mm. So width of plate is already given. Now we have done here B minus N. N is the number of holes. So B is equal to 200 and N is 3 holes. And what is the diameter of hole? Diameter of hole will be 22 mm. Okay, because this is M20 bolt, and we multiply it by 10. So this is my AN value, and the same value is written here. I hope this is clear to you. And this is the value of FU of plate, okay, not of the bolt, and this is divided by gamma m 1.25, and then you get the design strength of plate. Now the design strength of joint will be the minimum of design strength of plate and the design strength of bolt. So if we do a comparison between this 557 and 395, we arrive that it is minimum, so this becomes the strength of joint. Okay, now let us come to our second numerical, and in that it is asked to design a lap joint between 2 plates each of width 120 millimeter, and thickness of one plate is 16 mm and others is a 12 mm. Now this type of joint is a lap joint. So in lap joint you provide one plate like this and other plate like this, okay, and there is no use of cover plate as such. So you can directly do the punching work and provide the holes and then provide nut and bolts here, okay. So this is what it is done in the lap joints. So here in this case, although the thickness of plates are different, this is a 16 mm thick plate and this is 12 mm thick plate, so do not ask me to use packing plate here again, because packing plate will be used in butt joint, not in the lap joint, okay. Now the joint has to transfer a design load of 160 kilonewton, okay, this should be the design load. The plates are of Fe 410 grade. Use bearing type bolts. Now here it is also given, although it comes in the solution, that we are using M16 bolts of grade 4.6, or you can assume also, because this is a design problem, isn't it? Because here it is asked design a lap joint, okay. So how many types of problem can be? It can be two types of problem: analysis problem, in which everything is given, you just have to analyze it and calculate the capacity of joint. Second type of problem can be design type, and in that you will be given with the design load and you have to design the joint. And it depends on you what type of bolt you want to use, what grade and what diameter bolt and what gauge and pitch you want to provide. It depends on you. So in this case we have just directly used M16 bolts of grade 4.6. So diameter D is 16 mm, D naught is 18 mm and FUB is 400 Newton per mm square. See, all these things should be clear by now, okay. So I am going little fast. Since it is a lap joint, so the bolt is in single shear, okay, and the critical section being at the root of the bolt. So normally we assume that critical section lies in the threaded portion, because threaded portion are weaker. So that's why we put here 0.78 pi d square by 4, and area of shank region is put to directly 0, because this is a single shear, and this is the value of VNSF, okay. It is calculated in Newton. Now after calculating it, we have to calculate design shear strength. So this is the design shear strength of one bolt, okay. Now we have from the detailings we can take minimum edge distance that we have to provide is 1.5 D, and this is 27 mm, this comes out to be, and minimum pitch to be provided is 2.5 D, and this is comes out to be 40 mm. So this comes by experience also. So if we provide this value of end distance and pitch, then the value of bearing strength can be obtained. So first of all we have to calculate the value of KB. KB is minimum of these four values, which comes out to be 0.49, and when we calculate VNPB, it comes out to be this, and here we have used the minimum thickness of plate, that is equal to 12 mm, isn't it, and FU is the FUB here. So design bearing strength of one bolt is also calculated, and the minimum of shearing strength and bearing strength comes out to be this, okay. You can see, you can do a comparison. This is my shearing strength and this is my bearing strength. Which one is minimum? Shearing strength. So that's what we have taken here as the design strength of one M16 bolt. So this is written in the kilonewton. Now to transfer a design force of 160 kilonewton, how many bolts I have to provide? So the number of bolts required will be equal to total amount of load to be transferred divided by strength of one bolt, and it is coming out to be 5.5. So we can round it off to 6 bolts, 6 number of bolts, okay. So this is a lap joint, and how to draw the top view of lap joint? This is how we draw the top view of lap joint. Okay, so the dimensions are shown here, 16 mm plate and 12 mm plate, and this width is also given in the question, that the width is 120 mm. Okay, so this is what 60 mm gauge and 30 mm edge distances are kept, and these are the bolt number 1, 2, 3, 4, 5, 6, and this is pitch and this is end distance. So this is how the joint is designed. Now we also check for the strength of the plate, and the strength of the plate is calculated by TDN, and it is equal to 0.9 AN FU gamma m. So now the most important is AN, and AN will be equal to 120 minus, since there are 2 holes in the critical section, so we have subtracted it by 3 into, and M16 bolt is used, so diameter of hole will be 18, and this has to be multiplied by the minimum thickness of plate. So this is what is used here. I think you are seeing this. Okay, nothing to explain much, and this is the FU of plate, not the bolt. And when you do this, you calculate that TDN is even more than what we have designed for, 160 kilonewton. So you need not to worry, you have taken minimum side, and that is the safer side. Okay, now at the end we come to the eccentric connections, and eccentric connections with bearing bolts when load is in the plane of group of bolts. See, eccentric connections are different connections, and also we have discussed that lap joint is a case of eccentric connections. So here I have taken one case of eccentric connections, and here we have used bearing bolts, normal ordinary black bolts, and when load is in the plane of the group of bolts. So you have to visualize the diagram which I am going to show you. So this is explained as, if the line of action of the load does not pass through the center of gravity of group of bolts, the connection is said to be eccentric connection. Okay, so there is a plane of bolts, okay, and that is a group of bolts, and there must be a center of gravity of all those group of bolts, and if the loading is not passing through that center of gravity, but instead it is passing through the same plane but with a little distance, and that distance is called eccentricity, so such a connection will become a eccentric connections. So the first case can be that the line of action of eccentric load is in the plane of group of bolts, or second case can be line of action of eccentric load is in the plane perpendicular to the plane of group of bolts. So we have taken the first case here to understand, and this is a bracket shown here. This what you are seeing is a bracket, and on this bracket we can run another beam also. Okay, and this is my column. Okay, and here column is made with an I section. Okay, so I section, which I have already said you, are also known as beams, but they can be used for making columns also. So this is the flange portion of I section. Okay, and this dotted line you are seeing na, this is the web portion of I portion, so you may not be seeing it. Now on this I section I have connected a bracket with the help of 5 bolts. Now this is bolt number 1, this is bolt number 2, this is bolt number 3, this is bolt number 4, this is bolt number 5. Okay, so all these bolts form a group of bolt, and their center of gravity is here in the mid. Okay, so when we use a beam on this bracket, then of course the transfer of load from the beam comes to this point, and here it is the support of the beam, so the beam is supported here, so it is the normal reaction coming from the beam. Okay, so this is the force coming on the bracket, and this is at a distance of E, eccentricity, from this center of gravity. Now this P is resisted by these group of bolts by 2 forces. One is the linear force, which will be resisting P, and other will be radial forces which will be resisting the moment which is equal to P times E. Okay, first one is the simple force F is equal to P, and then there is moment P times E. So you all are seeing on each of the bolt, if you see, there is one force F1 in the opposite direction of this P. So P is acting downward, so F1 is acting upward on each of the bolts. Sorry, there are 6 bolts. This was the bolts, not the medium, this one was not the bolt, these are the bolts. So on this also there is forces being shown in the top direction. Then this moment is resisted by a radial force. So this radial force acts along this centroid, and you see at all the bolts this is the radial direction of forces, normal to the radius. Okay, so this diagram must be clear to you for understanding of analysis of forces. So by now we can easily do the simple comparisons, and here you can see the eccentric load P may be replaced by load P acting through center of gravity of bolts plus moment PE acting on the joint, and bolts are subjected to direct shear force, and shear force developed to resist moment PE. Now we can say that the load is equivalent to what? One axial load P and a moment PE. So if there are n number of bolts in the bracket section, so then we can say that this is the diagram when the load is lying in the plane perpendicular to the bolts. See, these are the bolts now. So this is the eccentric connection which is in the perpendicular to the plane of the bolts. Okay, but we are now discussing the first case only, and in that case the value of F1, which is the direction of forces in the opposite to the direction of force of P. So this F1 is acting on each of the bolt. Okay, and this is in the opposite direction of P. So this value of F1 on each bolt will be simply equal to P by N. If there are n bolts, so F1 will be equal to P by N, and it acts in vertical direction. It is very simple to understand. Now it is assumed that bracket is rigid, and therefore the force in bolt due to moment will depend upon its radial distances from the center of gravity of bolt and will act at right angle to the radial lines. So F2 will be directly proportional to radius, and F2 is equal to KR. If we remove this proportionality sign by bringing a constant K, so K is the constant of proportionality, and K can be found by equating resisting moment. So now this is the moment applied by the eccentric load P, which is equal to P times E. So when we do the summation of all moments due to this radial force, then this is equal to summation of F2 multiplied by the radial distance from the centroid is equal to P times E. So this equation must be clear to you. This is what is done, and F2 is kept here K into R, so it comes to be summation KR square, and this is equated with summation KR square is equal to P times E. So if we want to get the value of K is a constant, it will come out of the series summation, and K can be equated as P times E divided by summation of R square. Okay, so this is the value of K. Now we can calculate the value of F2. F2 was equal to K times R, and we can directly put the value of K here, which is equal to P times E and divided by summation of R square, and this has to be multiplied by R. So this is the value of F2, and F1 we have already calculated, it is equal to P by N. So F1 and F2, both the forces have been calculated on one bolt, okay, and both these forces F1 and F2 is in the same plane, because P is in the same plane, not the perpendicular. So we have to take the resultant force. And how do we calculate resultant force on a vector plane? We do the vector summation of two forces, because F1 is a vector and F2 is a vector, and there is angle theta, if you see in this diagram, between two forces. Here is also theta, if you see this angle is theta, this angle is theta. So that theta is also considered in this vector summation, and this is my resultant force F. Magnitude of this force F is equal to, resultant force F is given by root under F1 square plus F2 square plus 2 F1 F2 cos theta, and this magnitude of F force must be greater than the design shear strength of joint. And what will be the design shear strength of joint? It will be equal to design shear strength of one bolt multiplied by how many bolts there were? There were 6 bolts, okay, there were 6 bolts in that connection, and that we have to check here. So it may be noted that the farthest bolt is subjected to maximum force. So this is how we do the analysis of eccentric connections. So there are also many cases of eccentric connections when the loading is in the perpendicular direction, and that also can be discussed, because in that case tensile forces also develops on the bolt. But here a simple numerical is done for the eccentric loading on the same plane, and you can see the design strength of bolts in shear is calculated and bearing is calculated, and then we have calculated the minimum value of both the shearing and bearing strength, and it comes out to be this value. So we have calculated first of all force in extreme bolt, and F1 is equal to P by N, and in this case there are only 5 bolts. And then we have also done the summation of R square, and when we have put it in this formula of F2, and then it comes out to be this, and summation of F1 and F2 is done here, and cos theta is here, and this is the total shear force coming on the extreme bolt, because on the extreme bolt the forces will be maximum. So this is the extreme bolt which is subjected to this value of total shear force. Now we have just equated it to the strength of bolt, which we have obtained from simple calculation, and to satisfy this the P value must be equal to 59 kilonewton, okay, and total factored load on bracket will be equal to 2 times P, because there are 2 brackets, one on each faces of the column, okay. One bracket we are seeing where there is another bracket also on the back side, which we are not seeing in this diagram, because we are seeing only from the front side, but there is one more bracket at the back side. So there are 2 brackets, that's why the final load calculation is done here as 2P, and this is the total value of P which the bracket can easily hold. So this is all about the eccentric connections, and we will be discussing about the belted connections in the upcoming videos. So till that, stay tuned and stay safe. Thank you.